and at Berkeley, where he was a Simons Fellow. He has also held visiting positions at the Center for Mathematics and Computer Science in Amsterdam and the Economics Department of Oxford and Johns Hopkins universities. Georgios' main research interests lie in the areas of algorithmic game theory, computational learning theory, multi-agent learning, and dynamical systems. And as is clear from his very impressive track record, he's interested in exploring dynamic phenomena that arise from the interaction of numerous interacting adaptive agents. So needless to say that Georgios has made many contributions to this area, publishing in the best venues concerning AI, machine learning, and game theory research. And today he's going to talk to us about Beyond Equilibrium, a dynamical systems approach to learning in games, which should be really exciting. So with that, Georgios, I'm happy to hand over to you.
Okay, hi Carl, hi everybody else. First of all, thank you very much for the introduction. I am myself very much looking forward to the whole workshop. Can you hear me fine from your end? Okay,
yeah, I can hear you fine.
Great. All right. So yes, and thank you from on behalf of the whole community for organizing this. Despite all these hard circumstances, we really appreciate that. So, okay. Can you still? All right. Can you see my slides?
Yes, we can see them now. Yep.
Okay.
Thank you.
Okay, great. I can see no one. So please, if somebody has a question, maybe Carl, you can stop me.
I will interrupt you. Yep.
Thank you. Thank you. I appreciate that. Okay. I think I'm gonna hide this. Okay. So hi. My name is Georgios Piliouras, and as Carl said, today I'll be talking about learning in games and a systems approach, a dynamical systems approach to it that tries to go beyond the standard solution concepts of game theory and tries to explore new perspective and showcase their advantages in comparison to standard and more classical techniques. So, okay, I start my talk with almost a joking slide about what I consider to be the original sin of game theory. So here, of course, I'm talking about some fundamental results by von Neumann and Nash. Okay, the min-max theorem, of course, states that every zero-sum game has a unique solution, effectively unique solution. And then, of course, Nash's seminal result that every game has at least one Nash equilibrium. And I think what I find to be a little bit somehow negative about this kind of results is that they put us down a very specific line and way of thinking about what it means to study a game and what it means to understand game and social interactions and even interactions between AI systems, right? So to think about this, we sort of think of a game similarly the way we think about solving a optimization problem, like finding the truthful assignment to a satisfiability formula, right? So every single agent, is a variable. He has a correct somehow behavior, his correct assignment, and once everybody plugs in the correct assignment, you have that the game gets satisfied, okay? And that is in some sense a solution. But actually, I think a much more natural interpretation is to think of games as these inherently evolving systems. So things where agents, interact with each other continuously, and I think what's the most interesting thing that emerges is not some sort of static solution, but this, a very intricate coupling of behaviors. So, and you see somehow very non-stationary phenomena emerging across somehow wide social systems. And so the whole subject of my talk is to showcase some very specific, such interesting and non-trivial phenomena arising in some recent work, and hopefully trigger some interesting questions from, I would say, learning in normal form games to learning, of course, in the more complex phenomena of multi-agent reinforcement learning. And okay, today I effectively will focus on roughly these two different kind of categories of games. One of them would be games that somehow like model situations which are similar to traffic routing, and these are known as potential or congestion games. And of course, the very well-known categories of zero-sum games, things like rock, paper, scissors. And actually, even from the perspective of my talk, it would be a very simple example of a congestion or potential game would be sufficient. So and this is like, in some sense, the minimal example. So think of the two players as two balls, right? And this is in some sense the elevator game. You know, you can go to the left elevator or to the right elevator. And if you share an elevator with somebody else, then you have a cost of 1. And if you're by yourself, then you have, if you share an elevator, you have cost 2. And if you're by yourself, you have cost 1, okay? And so what we'll try to understand is we'll try to understand the behavior of somehow very standard learning dynamics in each of the settings, you know, and what's going to be interesting and instructive is that, okay, even somehow this in the simplest of possible settings that one can think of, you know, like very, very small games, just a finite, just a constant number of players, even 2 players, and even like a tiny number of actions, even like 2 actions per player. This would be enough somehow like to emerge, to see some very interesting dynamical system behavior emerge. And as we see, this dynamical system behavior, it won't just restrain itself in small, you know, somehow weird examples, but it will actually be very robust, and it will lead to new theories and new ways of understanding the systems. And okay, part of why I want to do this, you know, it's not necessarily somehow to, you know, because these applications are the most exciting applications of learning in games, no? But I really want to try to somehow to communicate these new vocabularies and new techniques, okay, new ideas, and somehow like maybe prime you to think about, okay, whether you've seen such behavior before in some of the systems somehow that you studied, and now maybe there's a keyword for you that you can you know, look into and maybe try to formalize this behavior, okay? So examples of behavior, of course, that we'll see are that of, okay, convergence that we understand, you know, periodicity, again, relatively straightforward, but then slightly more complex behaviors like limit cycles and chaos. And along this, there will be, you know, as I said, like a new series of somehow like technically more complex definitions. And as I said, like you don't have to worry about whether you've seen these definitions before. You know, we will cover them, you know, one at a time. Okay, and so let's start. So, and we'll start, I guess, with what we call like the vignette 1 type of results, where we'll be studying congestion games. Or another way to think about this is these are games of like common payoffs. You know, if something is good for me, it's good for you, and something is bad for me, then it's bad for you. And of course, this class of congestion games and potential games is, you know, arguably one of the most well-studied class of games from the perspective of multi-agent learning. So here, you know, I picked to, you know, perhaps selfishly, to cite like a very specific result of prior result of mine, old result, that says something that's like well known in the literature, that somehow if we study learning dynamics, which are like gradient-like, and multiplicative weights updates will be one of these dynamics that are both well known and will focus again and again for the perspective of this talk. Then, as long as this step size epsilon, this learning, this update step size is somehow small enough, then multiplicative weight updates in any potential game always converges to Nash equilibrium. But something that's actually not very satisfying about this kind of result is that in some sense, it's a kind of asymptotic kind of result. It requires agents possibly to be forced to learn with a really, really tiny step size. And this is something that, in some sense, it's not very, behaviorally sensible, right? So we really want players somehow to adapt to their environments. So they should be willing somehow to take larger step sizes. For example, if they're experiencing currently very high cost, and they can deviate to something else, okay? And the natural question here is to ask ourselves is that, okay, what will happen as we, let's say, use larger and larger step size? Would we expect somehow the robustness of this kind of equilibration result, or do we expect something, some sort of like phase change? The system could actually behave in new and unexpected ways. Okay, so that would be one of our first driving questions. And like to start with, and this goes back to a paper of mine, NeurIPS in 17 with Paleopanos and Panagias. Another thing that's actually well known about this class of dynamics, this multiplicative weight update dynamics, is that it has, at least two very common variants. So one of them, that we call like the linear version. So, and the other one is known as the exponential version. And it's easy to see that, this is in some sense a first order approximation. The linear version is a first order approximation of the exponential one, right? And again, the kind of setting that will be studied here is arguably the simplest possible setting, okay? So here are two players, so me and Carl, and we're thinking about like going to the left or to the right elevator, and, of course, as computer scientists, we'd rather be by ourselves and not say hi. So let's say we'll try to understand what happens if we start with some initial probability distribution, and then we keep updating our probability distribution as we experiencing cost on each of the two actions, okay? And again, to make everything here like super simple, both to simulate and to analyze, we always assume that the players here will have full information and they will see the expected costs of the individual actions, okay? So for example, if let's say both players choose one of the strategies with probability half, then this is going to be the Nash equilibrium of this game, and it will be stationary because both players see their expected cost. Okay, so this is the model, and what is already somehow kind of like super frustrating and indicative of things to come is that not only these theorems are kind of like unpredictable, but even these two somehow like almost identical learning rules have totally different behaviors. So in the case of the linearized version of multiplicative weight updates, one can show that a very, very strong convergence result, okay? So for any congestion game, for any number of agents, even if agents use arbitrary different learning step sizes, then this linear version always converges to exact equilibrium, okay? Extremely strong result, right? So we don't have to like fine tune for epsilon. We don't have to take infinitesimally small step sizes, and everything somehow like works as we would like, okay? But here's the thing is that, like, suppose, I'm sort of like coding this, quickly, like end of the day rush. And instead of like, coding the linear version, I actually code the exponential version, which is actually more typical in the literature. Then things actually go haywire, even in this minimal example, right? So the positive results for any congestion game. The negative results, we have that even in the simplest possible of these two balls, two beans game, then we can have that multiplicative weight updates can lead to limit cycles and even a formal notion of chaos that is known as Lior chaos, okay? And arguably, okay, I will go into the definitions of limit cycles and Lior chaos next, but what I want to say is that like this is like really, really bad news, So very simple example here, of course, it's trivial to compute Nash equilibria in a centralized way, but the learning dynamics actually can get confused and behave in a non-equilibrating and persistent non-equilibrating fashion. Okay, so to understand the theorem, we have to understand these two definitions of like what is a limit cycle, and then what is linear chaos. So what's a limit cycle? Okay, this is relatively straightforward. It's a kind of periodic orbit that trajectories converge to. Okay, so here's something like this, and typically we want to have like that. For a periodic orbit to be called a limit cycle, there must be at least one trajectory that somehow converges to it. Okay, as time goes to infinity. All right, so this is relatively straightforward. This is actually the most interesting and probably a definition you might have not seen before. This is this is not just any definition of chaos, but this is actually the very first formal mathematical definition of chaos. Okay, so to understand this, we have to have first a notion of what's a scrambled set. So given a dynamical system and some sort of like update rule, F, a pair of points X and Y, which are initial conditions for a dynamical system, is called scrambled if the trajectories that correspond to these initial points, they get arbitrarily close to each other. Okay, so the length on the infimum of the distance goes to 0. But then the trajectories then again will go apart again, right? So here's the trajectory of X, here's the trajectory of Y. As you move forward in time, they get very, very close and then far apart, very, very close and then far apart. Okay, infinitely often. Okay. So, and now this calls for 2 points. A set is called scrambled if this could be a larger set. Take any 2 pairs of this set. If all of them are scrambled, then the set itself is called scramble. Okay, and here's the definition of linear chaos. A discrete dynamical system is called linear chaotic if it satisfies these 2 different definitions. First, it has periodic orbits for all possible periods. Okay, so not just an equilibrium, which is just a period of 1, but a periodic orbit of period 2, of period 3, of period 1,000,001, and so on and so forth. Okay. So this is already a countably large set of non-equilibrium behaviors, okay? But it actually gets worse. The second condition that your system must satisfy in order for it to exhibit linear chaos is that there has to be an uncountably infinitely large set that's scrambled, okay? So, and this is really, really bad because from the perspective of, let's say, doing accurate simulations, because what's effectively the definition of scrambled set? So any 2 points in the scrambled set, you cannot tell them apart by simulate them. Because at some point, these 2 orbits become so close to each other that your computer will just get confused due to, let's say, accuracy issues. And then we won't know which one it follows. Okay? And now these kind of systems don't have just 2 such points that are legitimately distinct trajectories, but your computer cannot tell them apart, but effectively, uncountably infinitely many. Okay, so I claim that like this is, this is like a truly, truly unpredictable somehow behavior. And furthermore, you can show that this kind of game theoretic systems that we'll analyze also satisfy other standard notions of chaos, but I won't go into the technicalities of this. This definition will be more than enough. Okay. Now, okay, and I want to say something from the perspective of today's talk. Like typically, I like to prove things, but in this talk there are actually 0 proofs. So I apologize if you're really looking forward for like long mathematical equations. So all you see today is somehow videos, pictures, and simulations, because like I literally somehow I just want to show you phenomena, and I want to prime you about the existence of this kind of like, as I said, interesting behavior, and then maybe you can go out and somehow like search the space of all multi-agent reinforcement learning systems and try to identify similar behaviors or even more weird behaviors, right? And here's okay, my, I would say, proof by simulation. So just to make my simulation life a little bit simpler, I will start both of the agents, so both me and Carl, we start with a symmetric initial condition, okay? So we start with the same probability of using, let's say, the first elevator. And the reason I want to do this is because now it's easy to see that when we apply the same learning rule, this kind of symmetry persists. So the system effectively will have 1 degree of freedom, and now it will allow me to effectively simulate it very easily. Because all I have to tell you is, what is today, our joint probability of, our common probability of using the first link, okay? The first elevator. Yes, and then as I said, if we use the same learning rate, then this symmetry persists. Okay. So here's a first set of graphs somehow that we'll try to parse, and this is in the case where these two elevators have exactly the same cost. And let me try to explain a little bit like what is this first graph that you see. So first of all, the left-hand side of this picture corresponds to the linear version, the dynamic that somehow like equilibrates, whereas the right-hand side will always refer to the exponential version, the dynamic that somehow exhibits weird behavior. Okay, and now we look at the simplest possible example where the costs are exactly equal to each other for the left and right elevator. Okay, so what I plot in the on this first graph is effectively the update rule for after 1, 2, and 3 days. Okay, so for example, like if our common probability was 0.2, after one update rule, our common probability would have been increased to a little bit higher than 0.2, and the second line is what will happen after 2 days. The third line will happen, denotes what will happen after 3 days. Okay, and here this picture, we see what will happen after 10 update rules, given our joint initial mixed probability. Okay, and I claim what you see in this picture is a system that actually converges to equilibrium. Why? Well, because this point here, this point where the iterative map and the diagonal interact is exactly the equilibrium, right? So, and the Nash equilibrium is the fixed point of the dynamic, which is exactly the point where interact.
Quick question.
Yes?
Are you using a pointer here to point?
I am actually,
because I couldn't see it. But
I see.
There should be something if you go down in the screen where you have a virtual pointer.
Laser color, red. Yep. Let me try this. Can you see this now? Okay. Let me try to laser pointer. Let's try this. Okay, can you see this? Oh.
Yep.
Okay, great. All right. So these are the two. Okay, so these are the two important figures. So what I claim is that, like, okay, the red line is just a diagonal line, so don't worry too much about this. I'm just pointing out just to show you where the equilibrium is. So the Nash equilibrium corresponds to the 50-50 point. Okay, so if we both play 50-50, and when we update ourselves, we'll after 10 or 1 steps, we stay at 50. Okay, and that's why we have this point. But the other thing that's interesting is that, like, if let's say our initial common probability distribution was at 20%, then you see that roughly after 10 step sizes, we've almost reached the equilibrium value of 50%. Okay, so this graph tells me that this system within roughly 10 steps has equilibrated regardless of its initial conditions. Okay. On the other hand, if we play the exponential version, what do we see? We see the emergence of a limit cycle. Because it says that, like, okay, if our initial probability was, let's say, less than 0.5, after 10 step sizes, we have not converged to something that's approximately the equilibrium value, but something that's well off. Okay, whereas if we started above, we would be something like much larger. And if we run the next iteration and we saw iteration 11, then the graph would look like this. It will look like a step function in the other direction. And it goes back and forth. Okay? So a system that has, like, that within effectively 10 step sizes, reaches a limit cycle. What is more interesting is that, like, here's what happens if we change the cost of one of the two beams, on one of the two elevators. Now, instead of your cost being, equal to 2 when we're both together, maybe it's like 2.1. right? Whereas the other elevator still has like cost of 2. Then here's like the weird graph of what is our joint belief looks like after 10 iterations, okay? And what is obvious here is that like there's a crazy sensitivity of initial conditions, okay? So if initially somehow, let's say me with Carl started in this configuration versus this configuration, right? We have like totally different beliefs, even within like 10 days, okay? So we have the system has this sensitivity to initial condition, which is some like standard, indicator of chaos. Now, I actually I won't go into any, as I said, of the mathematical details behind how this result is actually being proven, but I do want to say that like all of this emergence of chaos is actually formal, okay, and it's based on this fundamental theorem by Lee and York back in '75, okay. But as I said, like today, I'm gonna focus on actual examples. And here, one could say, like, okay, this is just one single example, Georgios. Maybe maybe this is somehow like contrived. Maybe this is not something to worry about. But unfortunately, this in this very recent paper, we have shown that this behavior is not just robust, but in some sense, it's universal. So just don't take this, this very simple congestion game, but have something like that's arbitrarily more complicated. So now, not just 2 strategies, but like arbitrarily many strategies, and learn, have your agents apply this learning dynamic with any arbitrary small step size that you want, okay? Take any practical step size, something that like you could apply for your dynamics in practice, like 0.001 or something, okay? Then I can prove to you that if I keep adding more people in this potential game, if I add more and more people, more and more cars, in this kind of like routing network, then in every single one of them, you'll actually get a formal chaos emerge. And here, again, I give like a single example of, this is the behavior of let's say the fraction of the population that goes to, let's say, the top link on different days. So this is what the period 2 cycle looks like. So it's very dense, so you cannot see it going up and down because there's like 500 points here. But here you really see the emergence of chaos, right? So the number of people that go through the fraction of people that go through the top link just like moves like erratically over time, okay? And as I said, this happens everywhere. This happens in really, take your pick of a congestion game, you'll see this kind of behavior. And what makes this kind of theorem somehow like even weirder is that the time average, although the actual behavior of the day-to-day behavior is totally chaotic, if you look at the time average flow through each of these different paths, then it actually converts to the equilibrium flow of these games. Okay, so the day-to-day behavior totally unpredictable, but the statistics of the behavior totally predictable. Okay, so and there's even something that's even cooler, and actually I'll stay like at least a few minutes on this slide to try to explain this. And the reason why I really like this slide is because we also like studied not just the case of when you have an atomic game, which is you only have like 2 agents that interact on a network, but you can have a non-atomic game. So a game where you can have like, let's say, a continuum of agents. And it's well known that in this continuum of agents, in these potential games, there's a kind of like potential function that's strictly convex. So this is your potential function. And in some sense, the point at the global minimum of this potential function is this Nash equilibrium, the equilibrium flow of this non-atomic potential game. And this is known that this is unique, okay? So here's like the really, really cool behavior and I will explain this slide and this slide, okay? So suppose the population is relatively small. So what you see here is that the value of the potential quickly decreases, and very quickly you reach to the dynamics with its equilibrium that you see here, okay? So this is the equilibrium fraction. Let's say at equilibrium, let's say in the first link you have 75% of the people going through it, and indeed you see that the system stabilized very quickly. But now suppose that you keep adding more people in the population. Now initially the potential will decrease, but now it won't decrease all the way down to 0. It reaches a limit cycle right here. And this limit cycle in the potential going back and forth results in a limit cycle in the occupancy rates of different parts of the network, okay? Now I keep adding more people, it's like more and more, rush hour, okay? Now we go from converging system to period 2, and then we get period 4 and period 8, and so on and so forth. And we have this period doubling cascade to chaos. And within like a finite number of capacity, the system becomes formally chaotic, okay? So this period doubling route to chaos is arguably one of the most well-known phenomena in chaos theory. It's well known as a phenomenon known for the logistic equation that tries to capture how evolutions of fractions of species evolve over time, okay? But very interestingly enough, we got this in a game theoretic dynamic. And what is even more somehow surprising is that not only these dynamics are very robust, even beyond multiplicative weight updates. So we can show that this kind of chaos emerges even in the case where for much larger class of dynamics, like follow the regularized leader. And the one result that I really wanted to point out here is that we have something that's, I would say, totally crazy. That I can create a very simple game such that the dynamics, in these dynamics, the unique Nash equilibrium is locally asymptotically stable. So if you start close from the Nash equilibrium, all your dynamics actually converge to it. But the same very game also has provably chaotic behavior. Okay, so on the same game, so you can have and this is a result that it should be very scary about the kind of AI systems that we're building, right? Because typically we think that okay, look, if we have like a system and in our system at least the equilibria are locally stable, which is in practice what's the best thing we can hope to prove. I mean, hopefully we should expect that the system behaves well, given most initial conditions, okay? But actually here, we can create examples where that is not just not true, but is horribly not true, okay? So here's like the one initial condition, which is the red condition. We see the potential just goes to its global minimum, and indeed the dynamics actually equilibrate fast. Whereas another initial condition, just the dynamics just don't equilibrate and you get chaos. Okay, and once again, you can create this in absolutely minimal examples. Okay, and so this is truly somehow like a fascinating behavior that somehow like really shows that even a very well studied class of games like potential games with off-the-shelf dynamics like multiplicative weight updates and variants thereof, they can just behave in absolutely crazy ways. Okay. So, any questions so far? Or okay. So
maybe a quick question I have.
Yes.
The chaos in a congestion game series, is this through a bifurcation analysis?
So no, we use a different kind of analysis. So like a bifurcation analysis would just typically be used to show how how the Nash equilibrium somehow like goes from being stable to unstable. So here, it's kind of like it would be more typically a local kind of analysis. Where here somehow we have to use global arguments, and this is where the Lee York theory somehow like comes into play.
Okay. Yeah.
So right. Yeah. And I do want to point out something, actually, this is not the correct reference. I'm missing 2 co-authors, but I promise to fix it in an updated version that I can share with you.
There's another question that popped up.
Yes.
Georgios. Jayesh, do you want to ask your question? If you quickly unmute yourself. I can also ask it, obviously.
Yeah, so I was just asking, hi, Georgios. It's a fantastic talk. So in general, I mean, a lot of people are trying to apply these techniques to like a lot of real world problems as well. If you see a lot of interest in modeling intersection dynamics as Nash equilibrium solutions and a lot of these things. But like, so like when we analyze these games, like usually people have like discretized their action spaces and things like that. So like, is the analysis like about like when you discretize the dynamics, or like dynamics are assumed to be continuous and these results are the same, or like I don't know exactly the math.
Okay, that's an interesting question. So first of all, like all of the dynamics I've discussed here, at least their time is discretized. Okay, so this is just like standard, like it's like gradient descent. So the time is discrete, but the state space is continuous. So you assume that your state space is you evolve over mixed strategies, right?
Right.
So you could imagine that you could even discretize somehow like the state space, but these results actually won't go away. So what you could be able to prove is that, like, as you create finer and finer discretizations, okay, now you cannot really create formally somehow like chaotic behavior, because at the end of the day, your system would be finite, but you would create arbitrarily complex and very high periodic behaviors whose period can become arbitrarily large as you get towards finer and finer discretizations, okay? So there's really no hope to somehow like do some smart discretization and kill this kind of behavior, okay? This is indeed inherent.
I see, thank you, yeah.
I mean, the other way to think about this from just a practical, somehow like coding perspective, like whenever you implement something on your computer, like this effective discretization of the state space, like, you encode mixed strategies with some accuracy, right? And this is the kind of behavior that you see, right? So, yeah.
Yeah, good. Thank you, yeah.
Okay, so, all right, so this kind of, so the first vignette was actually about, these potential games and effectively games where your incentives are like perfectly aligned, right? In a potential game or a congestion game, we all act as if we want to, let's say, minimize or maximize this common potential. So in some sense, we're all in this together. It's a partnership game. So the second vignette that we'll be focusing on is the total complement of these games, which are like zero-sum games and slight generalizations thereof. Okay, and in zero-sum games, going back to what I said about the original sin of game theory. I mean, this is the one area, the one class of games where like economists go around like being like all happy, right? Because this is the prototypical success story. Okay, here is a class of games, and the games effectively have a unique equilibrium prediction. There's a well-defined value for equilibria and so on and so forth. Okay, and the story is, if only we could be so lucky, if only everything was as well behaved as zero-sum games. Okay. But now what we'll show is, zero-sum games are actually not well behaved, at least not well behaved from the perspective of, from the perspective that sees equilibration as this, as this forced unique solution of games and learning in games. So what we'll be discussing here is that okay, here we'll start with a simpler learning model where we'll actually make time continuous and not discrete. And this choice, although may look a little bit weird from the perspective of computer science, would help us a lot to create a formal theory of this idealized limit behavior as your clock runs in continuous time. And the reason why this will be helpful is because, we will show that these kind of systems, in some sense, develop formal similarities with systems in physics. So there's a notion of energy that's being preserved over time. And as a result of this energy preservation, the behavior will become oscillatory for all initial conditions, oscillatory again in a formal way that will make precise, okay? But what I do find somehow like fundamentally interesting is like, okay, this is a very clean mathematical result, but of course here, we're people who love working in dirty domains, right? So we love working with discrete time, of course, discrete space, really somehow like practical systems. And what is really interesting is like once you understand the behavior of this idealized continuous time behavior, you actually understand why the standard black box discretizations that people typically use when they train, let's say, learning in games, learning in zero-sum games, are actually formally can lead again to chaos. But how, by adapting and discretizations in different ways, you can actually get behavior that can behave, you can actually get performance that's much better. And once again, you can recover stability and predictability in these kind of systems. Okay. So yes,
I just want to flag that we are we roughly have 10 minutes left. We can go a bit longer because we started late as well. But I just
okay. Yeah. All right. Thank you for that. Let me just quickly go through, show you what I want to show you in terms of simulation. Okay. So here, once again, we will I will show you some simulations now, but not in discrete time, but in continuous time. So replicative dynamics is exactly this continuous time version of multiplicative weight updates. Okay. So now I will show you again some orbits, but these orbits now will be smooth. Okay. And here is this orbit of a replicator for rock, paper, scissors, where what you show here is, again, some initial belief for the red player, some initial belief for the green player, and how they evolve over time. And then like, a similar behavior for another set of conditions, okay? And what you see here is again, that the behavior, once again, is not equilibrating, it's doing something totally different, okay? And the interesting or somehow insightful thing about using these techniques from dynamical systems is you can formally understand what's happening in these games. So when you learn in games like rock, paper, scissors in continuous time, so games that have an interior Nash equilibrium where all strategies are played with positive probability, then given any open set of initial conditions, almost all trajectories that start from it return to it infinitely often. So what this actually says is that, like, look, like these trajectories are not perfectly periodic. They don't have to return exactly where they started from, but effectively they have to get arbitrarily close to where they started from again and again and again. Okay, and right, and in the case where the game does not have an interior Nash equilibrium, then once again you have a formal understanding of the theory. You just converge on some subspace of the game, and once again the dynamics perform this kind of cycling behavior. And this behavior is totally robust. So it doesn't just hold in these two-player, zero-sum games, but in holding arbitrary network generalizations of them. So you can have like many competitors. You can even have networks of competition that evolve over time, and analogous theorems somehow would hold. Okay. And again, the tools here come from dynamical systems, and they're not, I would say, so much, this is not so much somehow like the thing I want to stress with this kind of talk. But what I want to point out is that, like, look, here's a totally different kind of visualization that one could do, which effectively somehow like captures the cracks of the system. Okay, so what I'm showing you here is, and maybe I can start again. I took a set of initial conditions of my system. Okay, all of these like dark points. There's like 100 by 100 points, like very densely packed in the square. okay? And what I did is I had all of these points somehow like move forward in time according to dynamics. And the thing that somehow like drives this kind of behavior is that the volume of this initial set actually is preserved over time, okay? And due to this kind of observation, one can actually, again, formally prove that this behavior, will get this kind of like cycling kind of behavior, okay? So, and these insights, these connections with physics are actually formal, It's not just that these behaviors, these systems, they look like physics in an abstract way, but you can actually, write down a kind of vocabulary that translates game theory into things like Hamiltonian dynamics. So there's a notion of position and notion of momentum, and your game theory dynamics are effectively enforcing this kind of Hamiltonian evolution, okay? So I will show one last simulation, and this is the thing that I will stop with. Remember, in the previous example, I showed you the evolution of an initial set of black points, a set of initial conditions, and see what happens when you run this dynamics forward continuous in time. Now, I will do the same thing where the dynamics now run forward in discrete time, and this is actually the dynamics of gradient descent, okay? And what happens in the dynamics of gradient descent is that this initial volume of your initial conditions does not remain invariant over time, but actually increases, provably increases in zero-sum games, which is a mathematical proof of this butterfly effect. So it doesn't matter how much is your initial uncertainty about what was the correct initial condition, like very quickly your uncertainty explodes and your simulations are actually totally inaccurate, okay? But if somehow you understand the connection with physics, you're not going to simulate these dynamics. You don't going to go from continuous to discrete time the way we typically do in game theory and optimization theory. You will use a different kind of integration technique that's known as symplectic integration, okay? And the key insight here in this recent paper is that symplectic integration is not like some really fancy somehow algorithm, but it's just alternating gradient descent. So if you apply simultaneous gradient descent in zero-sum games, the system is actually chaotic. You have this exponential blow-up of any initial uncertainty, whereas somehow if you just this very small tweak, okay, like similarly with multiplicative weight updates, if you go from exponential to linear, here, if you go from simultaneous updates to alternating updates, the behavior actually totally changes. And once again, we get predictability, all right? So I'm actually gonna stop my slide deck at this point because I really want to say like, I really want to say what I came here to say and like what somehow like drives all of this kind of like, talk and this kind of discussion, right? So all of the results that I described today are effectively standard, literally like off-the-shelf learning algorithms in games with 2 actions and most of them with 2 players, okay? So I am mining like the very first type of examples of like learning games you could ever hope to mine, okay? And the kind of behavior that I see looks nothing like equilibrium, okay? So I can guarantee to you that like as we should, we go into the frontiers of multi-agent reinforcement learning, like, and here like our brave students, like go into the unknown, you should be guaranteed to see a wide plethora of very interesting non-equilibrium behaviors. In fact, the Nash equilibrium predictions most likely could be wrong and actually misleading. And misleading even in unpredictable ways. So you can have cases where all Nash equilibria would be locally stable and the dynamic will be chaotic, okay? Just think about this. Think about how many papers you might have written recently that just say, okay, look, we can prove local stability of some class of fixed points, and hence this machine learning system will behave well. Okay, and now I'm telling you, I can prove to you trivial examples where it passes the local stability. The game has a unique equilibrium, the equilibrium is locally stable, and actually almost all initial conditions will be chaotic. Okay, so we have to be cognizant about this kind of like, failure modes, I would say, of the theory of Nash equilibria, and record. We need more experiments. We need people to go out there and sort of like, I want to see simulations. Okay, here's my I just don't like to see only simulations where it's like, here's a graph and something goes to 0 or something goes higher, and like, oh, this is my new SOTA paper. Like this is like, of course, these are like very, they're very legitimate graphs, but like think of all of the different simulations I showed you today. Okay, all of these show a kind of behavior that we cannot see just by minimizing error, maximizing some function. It comes from a different perspective, and I think, look, either I'm really lucky and every somehow like learning game system that I put my hands on has like really weird, unexpected behavior, or these things are like super common, and I think it's the second. And at this point, I'll end and take any questions or invite any discussion.
All right. Let's maybe first thank Georgios for a wonderful talk. It's really great to see this. I think we can take time for maybe a couple of questions. So feel free to write your question in the chat, and we'll go over them one by one. I think Wolfram, you had a question. You want to unmute yourself?
Yes, thanks a lot for the great talk. I was wondering if you also consider noisy dynamics, or dynamics that have some stochasticity.
Yes. Okay, so I have some like recent upcoming work in this, and this once again gets even more interesting, because the correct solution concept at that point has to do with things like invariant measures. And again, this is technology coming from random dynamical systems, and this in some sense is the correct solution concept in these cases, right? So I give you, let's say, to give you like a very simple example, take the replicator dynamics or multiplicative weight-up dynamics and actually run them in a randomized way, okay? Now what you see is like you don't see a single orbit, you see a whole like, probability cloud that evolves over time, and you can try to think about, okay, what are the kind of like limit behaviors of this evolving probability distribution? And in this case, you would need things like invariant measures to do that, okay? So again, like the behavior will only become more complex as you introduce more complexity in the systems. And I agree, this is where we should be going, right? But I think there's still like a lot of very interesting behavior to be mined in deterministic dynamical systems. And what I really like it is it's such easy to communicate, you say like, okay, here's the system, simulate this, I know what you'll see, like, because there's only one kind of way that the system can evolve, okay? So, and I'm sure there's a lot of like very interesting phenomena that we still have not seen in deterministic systems. But I agree with you, the frontier and the thing that like, of course we're gonna attack is randomized versions of these systems. Okay, so you should work on it. So
I think he already might be working on that, actually. Maybe we have time for one or two more questions. Is there anybody who would still like to ask a question?
It's great to see so many like familiar faces. Like I really, it really feels like there's a lot of like friends and family involved.
Maybe one question I still have, and I mean, it's maybe. Something we have been discussing amongst us as well, but you're uncovering sort of all these stability problems and chaotic behavior problems with learning algorithms. Is that something like you see as maybe a sort of a hidden recipe that maybe could prevent this sort of phenomena?
Very interesting. Very interesting question, Carl. Like, let me see how, like, I actually think about instability. I don't necessarily think of instability as a problem in itself, you know? I think instability is actually, in some sense, like a power. Maybe it's a superpower of like multi-agent reinforcement learning, right? So maybe instability actually help us somehow like explore very large somehow like strategy spaces like very efficiently, okay? And for example, like, you know, without some specific type of instability, maybe not all type of instability, like, you know, like AlphaGo or AlphaZero would never find these like superhuman strategies in any meaningful time horizon, okay? If you think about this, you know, if you start with some initial, you know, with many different initial conditions, and all your initial conditions somehow like very quickly converge to a single point, you're not exploring enough strategies, okay? So I think instability could be a tool, okay, for sure. So it's not that you know, either system equilibrates or it's not useful. I think we really have to you know, like develop a different understanding of the systems. And as I said, the more we have tools about predicting their behavior despite non-equilibration, the more somehow we'll figure out how to actually use them to engineer stuff, you know, which should be our goal, you know?
Yeah, that makes sense to me. Yeah, completely agree. I think we have to round up here with our first invited talk. Georgios, thank you so much again for a wonderful talk, and give him a virtual warm applause.
I will.
Thanks so much. I think it is time